In this episode, we move into one of the most practical parts of cybersecurity work, because detection is where a great deal of defensive security becomes real instead of theoretical. A Security Operations Center, SOC, exists to watch for signs that something harmful, suspicious, or simply out of place may be happening across the environment. And that means the team needs reliable ways to notice danger before the business feels the full impact. For a brand new learner, common detection techniques matter because most incidents do not begin with an obvious public crisis. They begin with small clues, weak signals, and scattered events that only become meaningful when someone knows how to look for them properly. Once you understand the major ways a SOC detects threats, you begin to see that security monitoring is not about staring at endless alerts and hoping something looks bad enough. It is about using a set of thoughtful methods to turn noisy technical activity into evidence that deserves attention. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At the most basic level, detection means identifying signs that behavior in the environment may not match legitimate business purpose, expected system activity, or normal user behavior. That sounds simple, but the challenge is that modern environments produce enormous amounts of data, and most of that data reflects routine operations rather than attacks. A beginner should understand that the SOC is not searching for badness in a vacuum. It is comparing what is observed against what should reasonably be happening on networks, endpoints, accounts, applications, and cloud services. Common detection techniques are really different ways of making that comparison. Some techniques look for known bad patterns. Some look for suspicious behavior that breaks expectation. Some rely on context from past incidents or outside intelligence. All of them are trying to answer the same central question, which is whether the activity being seen is normal, mistaken, risky, or clearly malicious. That shared purpose is what ties detection techniques together, even when the data sources and methods differ. One of the oldest and most familiar techniques is signature-based detection. This approach looks for known patterns associated with malicious files, suspicious traffic, or previously observed attack behavior. The reason it remains useful is simple. Many attacks still reuse tools, infrastructure, file patterns, commands, and delivery methods that defenders have already seen before. If a file matches a known malicious fingerprint, or network traffic matches a previously identified exploit pattern, that can provide a strong and efficient signal. For beginners, signature-based detection is easy to understand because it resembles recognition. The system has seen something like this before, and it knows that pattern is dangerous enough to flag. At the same time, it is important not to overestimate this technique. Signature-based methods are strongest against known threats and repeated behaviors. They are weaker against new attacks, modified tools, and subtle misuse of legitimate systems. That means signatures are a foundational detection method, but not a complete one, because attackers change faster than static patterns can always keep up. A second major technique is anomaly-based detection, which focuses on activity that departs from what is normal for the environment, system, or user involved. Instead of asking whether something matches a known bad pattern, anomaly detection asks whether the behavior itself is unusually different from expected activity. A workstation that suddenly begins contacting rare external destinations every 10 minutes, or a finance account that starts accessing engineering resources at midnight, may deserve review even if nothing in that activity matches a known signature. This technique is powerful because it helps detect threats that have not yet been cataloged neatly or that intentionally avoid obvious indicators. It does, however, depend heavily on context and baselines. Without a reasonable idea of what normal looks like, the SOC will either miss meaningful anomalies or drown in harmless variation. For a new learner, the big idea is that anomaly detection treats change itself as a clue. The analyst does not need to know exactly what the attack is yet. They need to recognize that the behavior no longer fits. Baselining is what makes anomaly-based detection practical rather than chaotic. A baseline is the understood pattern of ordinary activity for a host, user, application, or network segment over time. It may include normal login times, common destinations, usual data transfer volumes, expected process activity, or ordinary application behavior during the week, month, or business cycle. Without this reference point, everything unusual starts to look equally suspicious, which is not helpful in a real SOC where unusual does not always mean harmful. A payroll system may transfer more data during one part of the month. A cloud service may become busier after a new deployment. A help desk account may log in from multiple locations in ways that would look highly suspicious for other employees. Baselining helps the team separate ordinary variation from meaningful deviation. For beginners, this is one of the most important habits in detection thinking. The goal is not to react to every difference. The goal is to understand what the environment normally does well enough that the differences that truly matter become easier to spot. Another common detection technique relies on indicators of compromise, IoCs, which are observable artifacts suggesting that malicious activity may have occurred. These can include suspicious file hashes, known bad domains, malicious IP addresses, deceptive email senders, or other concrete clues that have been associated with harmful activity. IoC-based detection is practical because it allows the SOC to search for specific evidence quickly across logs, endpoints, and network records. If a malware campaign is known to use a certain domain or file hash, the team can ask whether anything in the environment touched it. This approach is useful for triage, retrospective searching, and broad validation after a new threat becomes known. Still, IoCs have limits because attackers can change infrastructure, modify files, and rotate through short-lived assets rapidly. For a new learner, the helpful way to think about IoCs is that they are concrete clues, not complete understanding. They can point the analyst in the right direction, but strong detection requires looking beyond fixed artifacts toward patterns of behavior and intent. That brings us to indicators of attack, IOAS, and tactics, techniques, and procedures, TTPS, which focus more on what an attacker is doing than on the specific tools or artifacts being used. An IOA often reflects suspicious behavior that suggests a harmful process is underway, such as credential misuse, persistence creation, or unusual system tool execution. TTP-focused detection looks at how attackers operate, including the methods they use to gain access, move laterally, hide their actions, or reach valuable systems. This matters because tools and infrastructure can change quickly, but attacker behavior often follows recognizable patterns even when the surface details shift. A suspicious process chain, a sequence of privilege-related actions, or repeated internal discovery behavior may reveal an attack even when no single IOC is available. For beginners, this is a major step forward in understanding detection. Mature detection is not just about memorizing bad files or domains. It is about recognizing the kinds of actions attackers take when they are trying to establish control, avoid detection, and advance toward their objectives. Log correlation is another central technique in the SOC because many security events only become meaningful when multiple smaller clues are connected into one narrative. A single failed login may be nothing. A failed login followed by a successful login from a rare source, followed by privileged access, followed by suspicious process activity on a host, tells a very different story. Correlation works by linking events across time, systems, users, and devices so that the relationship between them becomes visible. This often depends on data collected from firewalls, endpoints, authentication systems, email platforms, cloud services, and applications, all brought together in a place where analysts can search and compare them. For a beginner, the key idea is that attackers rarely operate within one log source only. Their actions leave pieces of evidence in many places. Correlation helps the SOC assemble those pieces into something understandable. Instead of reacting to isolated noise, the team begins to see sequence, timing, and connection, which dramatically improves both detection quality and confidence during triage. Behavioral analytics is another important detection approach, especially in environments where valid accounts and trusted tools can be misused in ways that do not look obviously malicious at first glance. A user and entity behavior analytics (UEBA) approach examines the habits of users, service accounts, hosts, and other entities over time, then highlights behavior that falls outside expected patterns. This may include unusual travel patterns in logins, rare application access, strange timing, unexpected privilege use, or activity involving systems the identity does not normally touch. The value here is that many modern attacks involve using legitimate credentials or blending in with ordinary business tools, which makes purely signature-based detection less effective. Behavioral analytics helps the SOC focus on whether the action makes sense for that identity or system. For beginners, this reinforces an important lesson. Security problems do not always come from obviously foreign objects. Sometimes they come from familiar users or trusted systems doing unfamiliar things, and that mismatch can be one of the strongest early signals available to the defender. Threat intelligence also plays a major role in common detection techniques, because the SOC does not operate in isolation from the wider threat landscape. Intelligence can provide knowledge about current attacker infrastructure, emerging phishing themes, malware delivery methods, suspicious domains, and behavioral patterns observed elsewhere. When used well, this information helps detection teams tune their focus, enrich alerts, and search for relevant activity before a campaign fully affects the environment. For example, if intelligence suggests attackers are targeting finance staff with a certain style of document lure and specific follow-on network patterns, the SOC can watch more carefully for those signs internally. The important beginner lesson is that intelligence is most valuable when it improves context rather than simply adding long lists of suspicious things. A weakly managed feed can create noise. A thoughtfully used intelligence source can sharpen detection by helping the team understand why a particular alert matters, how it fits known attacker behavior, and what related evidence should be searched for next. Another common technique is rule-based detection, where analysts define conditions that should trigger alerts when certain combinations of events appear together. Rules may be simple, such as alerting when a high-value server contacts a rare external destination, or more complex, such as detecting a sequence involving email delivery, process execution, persistence behavior, and outbound communication. Rule-based detection is practical because it allows the SOC to capture known patterns that matter to the organization and apply them consistently across large amounts of data. It also helps translate lessons from past incidents into future visibility. If the team knows a certain chain of behavior has been important before, it can write detection logic to watch for that chain again. For beginners, rule-based detection shows that good monitoring is not passive. Analysts are not only receiving whatever the tools happen to notice. They are also shaping detection deliberately by deciding which patterns deserve attention, how broad or narrow the logic should be, and what level of risk justifies interrupting human analysts with an alert. Endpoint and network telemetry support many of these techniques because detection depends heavily on having enough evidence from the places where attacks actually happen. Endpoint data can show suspicious process chains, file changes, service creation, security control tampering, and account-related behavior on the host. Network data can reveal unusual outbound traffic, internal scanning, beaconing, strange DNS activity, and patterns of movement across segmented environments. A strong SOC uses both because many threats make more sense when host and network evidence are seen together. A suspicious process on a laptop matters more if that same laptop also began contacting a rare domain every 10 minutes. Likewise, an odd network connection becomes more convincing when endpoint data shows the process that initiated it and the file that started the process in the first place. For a new learner, this is a major takeaway. Common detection techniques are rarely tied to one source only. They become much stronger when they combine visibility from multiple parts of the environment into one coherent assessment of what is taking place. Tuning and alert refinement are also detection techniques in a practical sense, even though beginners sometimes think of them as cleanup work rather than security work. In reality, a noisy detection is often a weak detection because analysts quickly lose time and confidence when too many harmless events are treated as urgent. Tuning means adjusting logic, thresholds, exclusions, baselines, and context so that the SOC can reduce false positives without blinding itself to meaningful risk. This is an ongoing process because environments change, new systems are added, workflows evolve, and attacker behavior shifts over time. A rule that worked well 6 months ago may become far too noisy after a new application rollout. A threshold that once seemed safe may hide real risk after the business expands its remote workforce. For beginners, Tuning teaches an important truth about detection. Good detection is not something you build once and admire forever. It is something you maintain, question, and improve continuously so that alerts remain meaningful enough for analysts to trust and act on. Detection engineering is the broader discipline that ties many of these techniques together. It involves designing, testing, improving, and validating detections so that the SOC is not merely relying on default settings or vague hope that the tools will catch what matters. Detection engineering takes lessons from incidents, threat intelligence, business risk, and attacker behavior, then turns those lessons into rules, correlations, baselines, and workflows that fit the organization's actual environment. It also includes asking whether important threats would be visible at all, and, if not, what data or logic is missing. For a beginner, this is a valuable perspective because it shows that detection is a craft, not just an output. Strong SOC teams do not only consume alerts. They build better ways to see the threats that matter most to their business. That means detection improves over time through feedback, testing, and experience, rather than remaining a static collection of vendor defaults that slowly become less useful as the environment and the threat landscape evolve. As you bring all of this together, the lasting takeaway is that common detection techniques in the SOC are different ways of answering the same question. Does this activity fit what the business intended, or is it evidence of something harmful, risky, or suspicious enough to investigate? Signature-based methods, anomaly detection, baselines, IoCs, IOAS, TTP-focused logic, correlation, behavioral analytics, threat intelligence, rule development, telemetry analysis, and tuning all contribute different strengths to that answer. No single technique is enough by itself, because attackers vary, environments are noisy, and legitimate business activity can sometimes resemble malicious behavior until enough context is gathered. For someone studying CySA+, the big lesson is that detection is layered reasoning, not one magic alert. The SOC becomes effective when it combines these techniques thoughtfully, understands their trade-offs, and uses them together to turn scattered technical events into clear evidence that helps the organization respond before a small warning becomes a major incident.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.